Electrical principles. Trying to work on an electrical or electronic system without knowing the principles of electricity is like trying to fight a forest fire with a squirt gun. You would not be properly equipped to do the job, and you would get burned. This video will summarize the principles of electricity and magnetism. As a result, you will be better prepared to comprehend the numerous electrical and electronic devices that we use in our everyday lives. You will also begin to build a basic knowledge needed to master the diagnosis, service, and repair of more complex circuits. The atom is God's building block of nature. It consists of positive and negatively charged particles that move in perpetual motion. Protons are the positive particles, and neutrons are neutrally charged particles in the center of the atom. Electrons are the negative particles that spin around the nucleus of the atom. Everything around you, everything is made of atoms. A textbook, air, the sun, even you are made of atoms. Our solar system is set up much like an atom. Our planets, like parts of an atom, fly around the sun in orbit in a cosmic spinning dance. Normally, an atom has a balance of forces. However, it is possible for atoms to have extra electrons on their outer orbit. This extra or free electron is what produces electricity. In matter, billions of atoms can fit on the head of a pin. Depending on the organization and structure of atoms, some electrons can flow freely from one place to another. This is the basis of electricity. Electricity can then be defined as the movement of free electrons through a conductor. If you have a negative charge or excess electrons on one end of a wire and a positive charge or excess protons on the other end, electrical flow or discharge will result. Electrons will flow through the wire to balance out the atomic forces. To produce a simple circuit and use electron flow, you need a power source, conductors, and a load. The power source provides a source of electron flow. The conductors connect the power source to the load. The load converts electricity into something useful, light, motion, or heat, for example. A conductor is a substance that allows the flow of free electrons. Wires are a good example of conductors. They have unstable atoms that allow electron flow from one point to another. Most metals are good conductors. An insulator is a substance that resists or stops the flow of electricity. The atoms in insulators are very stable and do not allow easy electron movement. The insulation on wires, for example, is designed to prevent electrical flow out of the center conductor of the wire. You have probably seen the large insulators holding power lines to prevent current from shorting into its supporting pole or tower. Other examples of insulating substances are air, glass, plastic, rubber, and porcelain. There are three fundamental values of electricity: volts, amps, and ohms. Voltage is electrical pressure that pushes electrons through a circuit. Current is the flow of electrons. Resistance, measured in ohms, is the opposition to electron or current flow. Imagine two containers connected with a piece of tubing. Fill one container with water and leave the other container empty. Water will flow through the tube to equalize the amount in the second container. This is similar to electrical charges in a circuit that try to balance out forces in the circuit. A hydraulic circuit can be compared to an electrical circuit. The power source is like a pump that causes flow. The wires are like hoses to route the direction of flow. A control valve would be comparable to an electric switch. They both control flow through their circuits. The load is a device that uses the power source to do work. In the hydraulic circuit, a hydraulic ram would represent the load device and would be comparable to an electric load, an electric motor or solenoid, for example. Here we connected a light bulb to a variable power supply. As we turn the voltage up, electrons flow through the conductors, through the load or light bulb, and back to the power supply. This is the most elementary electrical circuit. A light bulb easily demonstrates the actions of electrons. Note the tiny resistance element in this light bulb. When millions of electrons try to flow through the element, some electrons strike each other and fly out, causing the emission of light. Here we are touching a power supply to a conductor to complete a circuit. As long as we have continuity, or a continuous electrical path, electrons will flow through our circuit. However, if we insert an insulator into the circuit, electrons will not be able to flow. There are no free electrons in the insulator. An ohm meter also demonstrates an open and closed circuit. If we touch the test leads of this ohm meter together, it shows 0 ohms or 0 resistance. There is a complete path through the test leads. When we do not touch the test leads together, an ohm meter would show maximum resistance, or an open circuit. This action is a basis for electrical tests with an ohm meter. Resistance, or ohms, is the opposition to current flow. Its symbol is R, or omega. Voltage, or volts, is an electrical pressure, or electromotive force that causes current flow. Its symbol is E, or V. Current, also called amps, or amperage, is electron flow. Its symbol is I, or A. Next, let's study how voltage, or electrical pressure, affects a simple circuit. Turning the voltage knob will let us increase and decrease the amount of electrical pressure applied to our basic circuit. A voltmeter and an ammeter are wired into the circuit to show the results. The action of the meters and the light bulb will show its effects. What do you think will happen to the ammeter when we increase voltage? As you can see, as we turn the voltage or electrical pressure higher, more current flows through the circuit and the light bulb glows more brightly. As we adjust voltage level down, less current flows through the circuit and the bulb dims. This demonstrates that voltage, current, and resistance all affect each other. Direct current, abbreviated DC, means that the electrons only flow in one direction. Direct current is used in low voltage devices like in a stereo, computer, or other electronic devices. Most of the wires in an automobile would also carry 12 volt, actually 12.6 volt, direct current. A graph can be used to demonstrate the action of DC. Here the direct current is off and the line on our graph is at 0. If we turn the switch on, direct current is applied, and the graph line would move up to show voltage. When we turn the power off, the line or trace drops back down to 0. Off-on-off, or alternating current, abbreviated AC, flows one direction, reverses, and then flows in the opposite direction. Alternating current is used in your home wall outlets for high power output. The wires in your house carry alternating current. Unlike DC, AC polarity cycles back and forth in the circuit. A sine wave is used to show alternating current. Note how the sine wave begins at 0, cycles positive, swings back to 0, and then goes negative. The electrons are reversing direction in the circuit from positive to negative. In our house wiring, this AC cycles at 60 Hertz or 60 cycles per second. This is fast enough that it cannot be seen with a human eye. A light bulb appears to be glowing constantly when it is actually turning on and off 60 times a second. If you connect a speaker to a source of alternating current, you can actually hear the AC as the current changes direction in the coil inside the speaker. This is the principle of how a speaker works. By changing current flow, the diaphragm moves and causes the air around the diaphragm to move. If we connect the same speaker to a source of DC voltage, you will not be able to hear the current flow reversing directions inside the speaker windings. Current will only flow through the speaker in one direction, and the speaker diaphragm will not vibrate and produce sound. You are probably familiar with a permanent magnet. This horseshoe magnet can be used to attract ferrous objects. Ferrous meaning iron-containing objects. Magnets come in various shapes and sizes. You can also use a coil of wire and electric current to produce a magnet. Magnetism plays an important role in the production and use of electrical energy. A permanent magnet has a north, positive pole, and a south, or negative pole. An invisible magnetic field or magnetic flux surrounds the magnet. When a piece of iron is not magnetized, its molecules are arranged randomly. However, when the iron is magnetized, its molecules align from north to south. The magnetic field can be used to act upon iron or steel. Even though the magnet is not in direct contact with the ferrous objects, these nails, for example, it can act upon them. The magnetic field will actually transfer out of the magnet and flow through and over the other objects. As you bring the magnetic field near the ferrous objects, it flows down and over the object and attracts it. Here we've taken and wrapped the south poles of these magnets with yellow tape and the north poles with blue tape. This can be used to demonstrate how like poles of a magnet repel and unlike poles attract. If we bring unlike poles together, they attract. If we bring like poles together, they will repel. Remember, like charges repel, unlike charges attract. A magnet can also be used to affect a compass. The Earth's gravity surrounding our Earth is similar in nature to the magnetic field around a magnet. Note how this magnet can be used to overpower the force of gravity surrounding the Earth and make the compass rotate. Here, we've suspended a large permanent magnet from a piece of string so that it is free to move. Permanent magnets have a tremendous amount of stored energy. Note how fast that magnet snapped against this person's finger. Also note how far the magnetic field transfers. It transfers several feet to attract the other magnet. What do you think the invisible magnetic field looks like? By placing a piece of cardboard over a permanent magnet and sprinkling metal shot over the magnet, we'll find out. Note how the invisible lines of flux extend out away from the magnet and actually hold the metal particles in the shape of the magnetic field. By moving the magnet on the other side of the cardboard, you can even see movement of the magnetic field. The thousands of tiny metal particles align in the direction of the invisible flux surrounding the magnet. Here we've taken a magnet and rotated it in front of a television picture tube. Note how the magnetic field distorts the electron beam as it tries to produce the picture on the television screen. Magnetic fields are used in literally thousands of different applications. Cassette tapes, videotapes, and even computer disks use magnetism. Tiny magnetic fields are deposited on the disks or tapes to store information. Electromagnetism is a branch of physics that deals with the interaction of electricity and magnetism. As this huge crane-mounted electromagnet demonstrates, electromagnets can produce a powerful force for doing work. Here we connected batteries to a coil of wire wrapped around a large bolt. When current passes through the coil, a magnetic field is produced. The nails are attracted to the core of the electromagnet. A considerably powerful magnet is produced by the batteries and the coil wire. When electricity flows through a wire, a tiny magnetic field is set up around the wire, but the magnetic field is very weak. An inductive meter measures the strength of the magnetic field around a current-carrying wire to make electrical measurements. For example, an inductive ammeter measures the strength of the magnetic field around a wire to determine and show the current flow through the wire. Electric motors use the principle of an electromagnet to spin an armature. Current flows through the windings in the motor, and the resulting attraction and repulsion of magnetism spins the armature at high speed. A solenoid is simply a coil of wire wrapped around a metal plunger. When current flows through the coil, a magnetic field pulls the plunger into the center of the windings. When current is disconnected, spring tension often moves the solenoid plunger back. Coils come in various shapes and sizes. They can also be used to increase or decrease voltage through induction. Note the hot, high voltage spark produced when this large coil is disconnected from the power source. Induction is when one current-carrying wire induces current into another wire. Primary current flow comes from the source of voltage. Induced current flow is a result of the second wire being close to the primary wire carrying current. Here is an interesting experiment. Take a coil, connect it to a source of alternating current, and watch what happens to this aluminum ring. The magnetic field actually makes the aluminum ring levitate above the magnetic field. The atoms in the aluminum are repelled by the magnetic field. Other videos in this series cover electrical and electronic theory and troubleshooting in more detail.